Hello everyone, my name is Bartlomiej Waszak. I'm a senior software engineer at Respawn. Thank you all for joining us. Today we are going to explore different gameplay programming patterns. In this presentation, I'm going to deep dive a bit more into some of the specific patterns and some specific solutions we can use when working on the game. And at the beginning, I'd like to share an inspiration I had for this talk. So I'd like to highlight 4 very different games I had the pleasure to work on in my life. So Assassin's Creed Syndicate and the open world, action adventure, Star Wars Jedi Fallen Order, first-person shooter Alien Rage, and a mobile title I Must Run. And these games, they are really very, very different in terms of gameplay, team size, and programming tools. But still, I learned and discovered that actually there are some common patterns in gameplay programming, and people use some common solutions to very specific problems. And this is what I want to share here in this presentation. So very shortly, what I'm going to talk about today. So I'm going to talk about data structures and data design, managing resources, prediction, state machines, physics, and some optimization tips. So let's start with the first chapter, data structures. So first, what actually we want to avoid when we work with data structures. So the first thing to avoid is actually dynamic allocations of your memory. Because usually when you need to allocate some memory, it needs to be requested from some memory manager from heap. It may involve some memory fragmentation problems or some multi-threading issues, and it involves a lot of underlying operations to do this operation. Also, what we would like to avoid is non-linear random access to memory, because it really gives us poor usage of CPU cache memory. And when we learn at school about different data structures, usually we start with some linked lists, double linked lists, we go to queues, stacks, trees, graphs, and there are even more complex data structures we learn about. But actually, the most common data structure in game or gameplay programming is just an array. And why actually arrays are so good? So first of all, they are very simple and easy to use. It's like straightforward implementation and interface. They give something that is very important from the performance point of view. So iterative access in the memory is the best usage of CPU cache memory. So usually when we access one element in an array, let's say how we have here at the index 4, there's much more memory loaded to CPU cache. It's a cache line. And it means that another element after 4th element will be loaded much faster, and we can access them way much faster than just randomly choosing different areas in the memory. So it really gives us the best usage of CPU cache memory. And also, they are very flexible from the memory allocation point of view. We can have like static size, dynamic size. And going further with memory allocations, I like to specify what I mean by that. So at least we have a few options we can use for arrays. So we have memory allocated on the stack, like we have here with that array A. So this is array with 8 elements. This is very fast because we are allocating it on a stack immediately when we enter that function. But unfortunately, it's just a fixed size. We just have exactly 8 elements. We can also allocate memory for the array on the heap. So here I'm just using new operator, and I can specify the size during the runtime. And we have also more complex implementation for the array. Here I'm using std vector. Under the hood, it's still using dynamic allocations on the heap. It's much slower to use it, but we have dynamic size of the array, and we like the array grows whenever we add more elements. More elements are allocated on the heap, and if we need bigger size, we need to copy elements from the previous allocation to the new allocation. So there are much more memory operations involved here, but we have dynamic size of the array. And actually, in almost every engine I had worked with, we can take the best of both worlds. And here is the example in Unreal Engine 4. So we want to have something that connects the fast allocation of stack array and dynamic size of allocation of the array on the heap. So what we do here, we specify for the array D here additional inline allocator with parameter 8. What it means? It means that the first 8 elements for this array will be allocated on the stack. So we have very fast access to these elements, and this memory is allocated in a very fast way because it's just on the stack. And if the array grows with more elements than 8, then these elements are allocated on the heap. So here we can decide that usually I don't need in that function more than 8 elements. So I think that 8 elements will be enough because I know what that function will do. So I want to use stack allocation for 8 elements. But sometimes I need to still support more than 8 elements. In that case, I'm willing to use heap allocation. So this is something that mixes both types of allocation, but still we are using the same interface to access our elements, and all the allocation logic is running under the hood in T-array and in T-inline allocator. Another important thing with arrays is that we can perform removal of the element in 2 different ways. Let's say here I have the array that I want to remove the element at index 4. So what I need to do here, after the removal, I need to shift every element after 4th element to the left. So it involves the copy operator for every of these elements. So this is kind of costly operation usually. But I can do it also in the other way. So what I will do, I don't need to keep the order of elements in some cases. So what I can do, I can just swap the last element in that array and put it into the place of that 4th element. So every element after the element at index 4 stays at the same place, and I don't need to involve any copy operation. This is faster, way much faster, because it involves just copying one element, but unfortunately in that case the order is changed. If I don't need to keep the order of elements in my array and just treat my array as a set of elements, then this second operation for the removal of element is way much faster and is much more useful in that case. So this is very important to remember, that actually we have 2 ways how we can remove the element in the array. And I would say that probably 90% of data structures in games are arrays. But if you are looking for like the second most common data structure, the one that you would like to learn more about, I would point to the map. So this is like a dictionary, and so it supports like adding, searching, and removal of the element. And this is very common use case for maps. So we kind of associate some object ID or some primitive type with some associated data structure, and we create that kind of collection. So this is a very useful case when we can easily search through some associated data depending on particular element using just that element ID. So this is very common case, and I'm really like encouraging also to explore and learn this kind of pattern for data structure. So a short summary for our data structure. So know your arrays. It's really important data structure, and deeply understand the interface with implementation, because actually most of your time you will work with arrays. So this is very important to know exactly what's happening under the hood. And if you would like to read a bit more about arrays, here is the link to discover even more for arrays in Unreal Engine. So now we go to another chapter about data design. So this is like a very basic example we start with. So we have a weapon component and 3 properties in that component. So like parameters with reload time, recoil, and magazine size. So it is like in almost every engine you can find some way to expose these values in the editor, so that designer or programmer can tweak these values very easily. And access to these parameters usually is also very easy in code, just by accessing a variable usually. This is very like basic way of working with the editor and designers, and how we want to like expose some values for designers. But this is like very basic approach, and usually what's more better approach when we think about shipping solutions for the real game is actually to separate parameters into a different class, to a different data structure, so that runtime component, runtime class, like we have here, that weapon component, is just referencing weapon parameters, which are a separate set of values, and still access to these parameters is very easy. For example, here through a pointer. But what it gives us is that this is much more designer-friendly way of specifying some parameters, because we have these runtime classes on the right, and we have this set of parameters on the left, which are much more designer-friendly, because they are just really dealing with behavior of the in this case of the weapon, and it doesn't need to mix some other variables that could be, for example, a programmer value or some programmer variable, which is not very important for a designer to be dealing with that. And also we can have potentially multiple runtime instances of logically the same weapon, so we can reuse the same set of parameters, for example, one weapon in different instances. So we are just linking from the runtime class to that set of parameters, which is the same for all instances. And also in that case, it gives us very easy and flexible way to, let's say, we want to tweak a bit and change one weapon when it is used by AI instead of the hero. So we can easily just swap references depending on who is actually using the weapon in the game. And also going further with that, there's a pattern that we can use how to like define more complex data from designer point of view. So this is like sharing the same root, and so that multiple instances of let's say weapon parameters will share some base set of parameters which is like unchanged depending on different types of the weapon. So this is like that we want to share the same data for multiple weapons and just change some smaller subset of values for specific kinds of weapons. So this is very similar how inheritance work in programming. So we have some set of base parameters for the weapon, then we derive from it a set of more specific types of weapons that we just change some smaller subset of numbers here. And also we can derive even further so that we have like one type of weapon that is again being used by AI instead of the hero, for example. And in that case, we just change maybe a few parameters here. What it gives us, that overall structure, is that when, for example, near the end of the game, when we have, I don't know, maybe 20, maybe 50 weapons in the game, when we want to change just one parameter, even just slightly, but in every weapon, it is really difficult that we would need to modify that one parameter in every instance of that set of parameters. So instead of that, we could just modify it in one place, in that case, in weapon-based parameters, and it would be inherited by every other weapon in our game. So this is very also common way how we like define set of different parameters for a set of objects. So this is something very useful, especially when we think about scaling the data and scaling our game. And also, this is more like sophisticated way of approaching some data control for our game. So in many cases, there is a situation when some simple linear dependency is not enough when we want to control the behavior of something in the game through data. And actually we need more advanced, more complex way to control specific value. And in that case, this is here we have like a collision, like let's say we can imagine a vehicle driving in the city, and what we need to do, we need to apply some damage points on collisions. Whenever we drive into something and collide, we need to apply some damage points to the vehicle depending on the collision amount, so how big the collision was. And we can think here that, yeah, like simple linear dependency on the left, it would be enough. So just take directly collision amount and multiply it by something, and we have damage points as the output. But actually, when we play the game, we realize that it's actually not enough for what designers want, because for smaller collisions, I actually don't want to punish the player at all. So for some collision amount, I don't want to apply any damage points at all. Then at some point, I want to start applying damage points, but very slowly. I still don't want to like punish the player too much. But then at some point when collision amount are really high, I want to actually like punish the player more, because I want to say to him, yeah, this was something bad, you shouldn't do it anymore, unless you want to break your vehicle. So then I'm applying this steep curve, and I'm really raising damage points very fast. And then at the end, I'm again like dumping this value with some maximum number for the damage points. So this is the curve on the right, and this actually represents much better intention from designers, what they want to do with the specific logic and specific behavior. And this is also very common that many times you start with some behaviors as a simple linear dependency, like the graph on the left, but you actually end up in the final game, you end up with something more complex, which is the curve on the right. So if your technology allows you to specify in data these kind of curves or just draw it in the editor, this is something very useful, and it can really can really give you much more sophisticated behavior in your game. So short summary for data design. So first of all, it's really good to think about what should be exposed as data in your editor or your scripts, because sometimes just exposing too much with something that could be really left as an like constant value in your code, sometimes it's just too much for designers, and it can create really very unstable code when everything can be changed from data. It's also very dangerous. So it's really important to plan at the beginning and think about what should be actually exposed in the editor, and make it easy for designers to manipulate data. Plan for scaling the data and plan for fast iterations. So try to create those separate set of parameters that leave as separate data assets that can be easily tracked, and you can use some form of inheritance in data to easily manipulate bigger sets of your parameters. So now we move to another chapter of our gameplay programming patterns. I'm going to talk about managing resources. And mostly what I'm going to talk about here is about spawning and despawning. So let's say I want to create a new special effect, a new sound. I want to create some new object or a new character or a new vehicle. And spawning usually is very costly operation in most engines because it requires some allocation, memory allocation, some allocation of resources, loading of meshes, textures. It requires initialization for a lot of code and data. So usually this is a very, very costly operation. And there's a solution for that, very commonly used in many different games, which is called pre-allocated pool of objects. So what I want to do here is, instead of spawning and despawning, we'll use only activation and deactivation on already spawned objects. And depending on the needs of your system, we spawn our pool of objects just once at the beginning, let's say during loading the world, and we will just reuse these objects during the gameplay. So we can think about this kind of pre-allocated pool of objects as a kind of middle layer between engine spawning and gameplay use cases. And here I have an example of the pool of special effects. So let's say I have 4 explosions. So I load and create these special effects somewhere during the initialization of the game or loading your world. And whenever I want to create and trigger the explosion somewhere in the game, instead of loading again all the assets, I am just moving and placing that explosion and taking it from the pool and moving it somewhere in the place in the world where I want to trigger the explosion, and I just activate it. So normally these like objects in the pool, they can reside somewhere under the ground, and they are deactivated, so they are not really like running, but they are loaded and ready to be used. And whenever I need to trigger the explosion, I just move it to the place I want it, and I activate it. So in here, let's say I have really big action in my game. So I have like 4 explosions, one after the other in a very short amount of time. And there's like common situation and common problem, what to do when I want to like spawn, I want to create even 5th, another explosion. So in other words, what to do if all objects are active and we need a new special effect. So usually there are many solutions to that problem, but usually we still don't want to like load and spawn another explosion and dynamically allocate resources for them. But actually we still want to reuse one of these 4 explosions. And what we want to do, we want to just choose one of them, one of these 4 explosions, and deactivate it and move it to the place where I want it again and activate it again. So I want to choose one of these explosions, which is like the least noticeable for the player. So I'm looking for like time since last activation, some distance to camera, or some other priority, to choose the one which would be the least noticeable for the player to disappear somewhere and appear in another place. Usually when we have like 4 explosions running almost at the same time in your game, when one of them disappears somewhere and appears in other place, it's kind of hard to notice when already we have like a mess on the screen, and in this way we are still just having 4 explosions like running at one time in the game, and we don't need to allocate any new resources. There's also another way of approaching the same problem. We can actually have 2 pools, so high quality pool and low quality pool. So we have high quality pool with like high quality assets, with maybe bigger textures, with higher quality logic for special effect. But we have just 2 of them. And normally when there's just 1 explosion or 2 explosions, that's very simple because we are just reusing these already spawned explosions, very easy. But what if we want to have 3 explosions? Then we have another pool, but this time of low quality explosions. So maybe like logic for these effects is much more simpler. They are using much simpler resources, so they are consuming less memory and less time to activate them and to run the logic for them. And usually when we have already like 2 big explosions on the screen, when we have like another 3rd and 4th explosion, which is maybe a bit lower quality, it's really hard to notice if there is something different, because we have a mess on the screen. So but it keeps us really without any costly spawning operations, and just simply still reusing the same assets and the same objects all the time. So pool of pre-allocated objects is really very effective way to minimize the cost of allocating resources. And it's important also to say that we should use this kind of technique for frequently manipulated objects, because here we are kind of sacrificing memory allocation and gaining performance, because we don't want to spend too much time on spawning and despawning and allocating all these resources. We have them allocated already, so they occupy the memory all the time. So this is not something that should be used on very rarely used objects, because they would be in the memory all the time. But this is something for very frequently manipulated objects in the game. And also, it is a nice way to enforce some budget limits for your runtime code. So we can always be sure that there are no more specific elements in your runtime behavior, like, for example, the number of explosions. So this is for like our design pattern for managing resources. And now I want to move to prediction. And what I want to talk about here is mostly movement prediction. And actually, we need to use movement prediction in our game, in our games, much more often than we could expect, because that's very common thing to do in real life, actually. And when the game tries to imitate the real life and do similar things, we also need to use prediction in our games. And for example, we need to predict the trajectory of grenade to allow NPC to avoid it. Otherwise, NPC would look very stupid when he is like, or she, running very directly at the point of grenade to be killed by it. Also, like the position of the character when we want to fire some projectile towards it, or a movement of a vehicle for some jumping and to predict landing position for the jump, or a position of the vehicle when we want to avoid the vehicle for NPC in the near future. And also for replication in multiplayer, that's very common technique to predict the movement of usually characters, because we usually don't have so much data in multiplayer, so we need to compensate with prediction. So I'm going to talk about 3 specific types of movement prediction. So the first one is the simplest one, so it would be for the movement of the character. So in this case, I just want to predict where the character is going to be in the near future. So let's say after half a second or after a second. So here I have a position of a character at x0, and I need a velocity v and time t, which is like the time of prediction I want to have in the future, and x will be my predicted position of the character in the future. So this is a very simple equation, but it gives us nice prediction of where character is going to be in the near future. Another case in this situation, much more complex, is when I'm throwing a grenade and I want to know where it's going to land after a few seconds. So usually in that case, I want to involve collisions. So here is very simple loop how we can like predict where the grenade is going to be after a few seconds. So here we have like very simple physical simulation, because that's basically how we should approach this problem. So I'm computing every step, I'm computing velocity and position change, and I'm checking if between the old position and the new position, if there was any collision. And if we have a collision, then I need to have impact normal from that collision point, and I need to compute how the velocity should change after the impact. So this is what's happening in that if statement. And usually I'm repeating that operation for the specified amount of time I want to know before the grenade should explode. So this is very simple loop of physical simulation, but it gives us quite good approximation of how the trajectory of the grenade is going to look like. And the third case will be different, because I want to know for vehicles not only linear movement, but also angular change. So usually for vehicles, because they are rotating and moving quite fast, I need to include some angular movement for movement prediction, even for like a short time in the future, let's say 1 or 2 seconds. And here is a very simple way how we can apply a rotation change from angular velocity to our current rotation. So rotation angle and rotation axis is extracted from angular velocity. Then I am creating a quaternion from that rotation axis and rotation angle, and I'm multiplying current orientation with that new computed quaternion to get the predicted orientation in the future. So that gives me an angular change and how the rotation will change for the vehicle in the closest future. So shortly, summary for movement prediction. So we as humans, we actually predict the movement of objects all the time because we kind of think about it that whenever object is moving, we can not only think about its current position, but also we know where the object will land in a very short future, because we can kind of predict and like compute that movement in our brains. And we need to do and should use it in our games also, because I want to know and apply some gameplay logic depending on where specific objects are going to be in the near future. So let's say if I'm throwing a ball, I'm not running toward the position where the ball is right now, but actually if I want to catch it, I'm running to the position where the ball will be in, let's say, 1 or 2 seconds, where I can really catch it, because I know that it's not going to land in the place where it is actually right now, but in the place somewhere farther along the velocity direction. So that's why this is something very common actually in games, that we are having the same behaviors, and we need to write gameplay code which is very like depending on that movement direction. And usually this kind of like movement prediction requires some form of physical simulation. And if you would like to read a bit more about movement prediction and have more details, I wrote an article on Gamasutra, and here is the link. You can read further this document. So now I'm going to switch to the next chapter, so state machines. So this is very simple but powerful concept, and probably every one of you heard or used some form of state machine in your programming. So this is really like a tool to simplify the flow and organize the code. And actually a lot of gameplay code can be described in terms of the state machine flow. And being a gameplay programmer or working as working with gameplay means really working a lot with state machines. So this is a very important concept. And basically, like, every Boolean variable is a part of some state machine, even if it is not expressed directly. So how to approach designing state machines? So it is really crucial to write and to think about proper design for state machines, because we want the code to be easy to read, to debug and maintain. So we should identify main states, substates, and code that should be inside of these states, and the code that should be still left outside of the states hierarchy. So in the classic approach, when I think, let's say, about human behavior, and I have here like example of human state machine. So I think about states like walk, crouch, crawl, fall, jump, and others. And in a classic approach, I would have like a lot of Boolean variables, for example, like if I'm in a crouch state or if I'm falling, and depending on these variables, I have a lot of conditions in code. If it is true or false, I'm doing specific things in different various places in my code base. So in this way, we can end up very easily with a messy code and hundreds of places with those conditions, and the flow of your like states is very unclear, how one state changes to the other. So it's really good to have more specific definition of your flow, of your execution flow for your states. So it is better to strictly define state machine, and we can do it in a very different ways, and there are a lot of different ways how we can implement state machines. Here is just an example to give you better like perspective, what I think about state machines and how they could be used effectively in your game. So it is very good to strictly define the code for entry point, for update step, and exit point. So here I'm thinking about crouch state. So I have 3 methods in my state machine: crouch, enter step, state, update step, and exit state. And we should put, this is very important, we should put the state related code into the state function instead of spreading that code somewhere else. So it's really about whatever is crouch related in your game. As much as possible, it should be placed in the crouch state, not somewhere else in your game, so that all the functionality for the crouch in that case is encapsulated in my state, in human state machine. And also actually a lot of important code will end up in your transitions method. So entry point and exit point methods. So for example, here in my crouch enter state, I want to inform animation graph that yes, I'm starting my crouch state. I want to do the same with my sound manager. I want to start playing the sound for crouching, and I want to inform camera that I'm starting crouch and I should switch to some special mode. And very analogically for exit state, I want to inform camera and animation graph that right now I'm stopping crouching. And it's really interesting to see when I was working with state machines and creating state machines that it's really good, and it's very normal that we have a lot of code actually written in these transitions, in these enter state and exit state methods, and very little actually in the update step. And this is really good from performance point of view, because the transition methods, we are just executing once when we enter the state and when we exit the state. And update step, we execute all the time when we are in a specific state of the state machine. So for example, we could also play sound on the entering the crouch by using some update index when it is 0. Yeah, I know I'm starting the crouch, so I want to play sound. But you know, that's not the best way of doing it, because we would check that if statement every iteration of the update step method, and it is really much better to use enter state method to execute that sound. So summary for state machines, this is really like very important concept, especially for higher level gameplay programming. And I'm really encouraging you to try in your engine, in your code, in your data, some form of state machine, and think about it, what's the best design for your particular case. Because good design for state machines, it kind of encapsulates functional parts of some specific feature in your state or some multiple states. And it makes the code much easier to read and to understand. It really clarifies the flow of the execution of your logic. And your transition methods are really important because you should really actually use these places to write some important code there. And at the end, I have very I have a reference to my previous presentation at Digital Dragons 2016 about gameplay programming in Assassin's Creed Syndicate. I'm giving there a few examples of state machines that we were using in that game for vehicles. So if you are looking for some real world examples, how a state machine works and how the design looks like, I'm really encouraging you to check that presentation. So now I'm moving to the next chapter about physics. And here I want to focus on one of the most expensive parts of the physics, which are physical casts. So I'm thinking here about like ray casts or shape casts using capsule or box or some other shape. And typically we have like limited amount of data as an input and output. So we have for ray casts, we have like line start point and line finish point, and we have some collision flags, and we get as the result collision point, collision normal, some object reference. And this is very important to be careful about choosing correct input parameters. So the length of the cast, longer lines, longer casts, or the size of the shape, it generates significant cost for the physics engine. So it is very important to correctly choose the size of the cast. And collision flags, we want to search through like static objects, dynamic objects, some debris or characters. This is very simple and effective way to limit the cost of the physical cast. So it's really important to know exactly what you are looking for physical objects and to filter out unnecessary objects, because it will make it much easier and much faster for physics engine to give you the results you are looking for. And another thing from performance point of view is trying to avoid doing too much physical casts in one update step. So for example, we could try to limit number of casts to one in one step. So here on the left, I have 2 casts in one update step. So I have line cast for the detection of some interactive objects in front of me, and I have a capsule cast to detect some objects very close to me. And what we can do here actually better is that we can alternate and just trigger one cast in one update. So on odd and even frames, alternating between line cast and capsule cast. So every cast is executed every 2 frames. So we never really run 2 casts on one update. So it gives us a little delay with getting the results. And usually for these cases, nobody will notice, the player will not notice that you have just 1 frame delay, but you are actually avoiding half of the, or approximately a half of your time performance cost for physical operations here. And we can go actually further with that concept. Let's say we have a lot of different objects in the game, and all of them have some physical requests for some casts. And in many cases, we actually don't need these results immediately. And we can specify, the clients can specify how many frames they can wait to actually get the results. Because in most cases, results are not needed immediately, but they can wait 1 frame, 2 frames, or even maybe 5 frames for results. And what I want to do here is that I'm collecting all requests for physical casts in my command queue. So all of them, I just gather and collect just the requests. I'm not executing any casts yet. And I'm writing a wrapper that executes batched casts. So I'm taking all these cast requests and I'm sorting them using some priority, and I have some like a budget defined how many physical casts I want to perform in one frame. So let's say 5 casts or just 10 casts maximum in one frame. And then depending on that wrapper just takes my request and executes it in one place to the physics engine. And once I get the results, I'm giving it back to the clients after the cast is executed. So it could be a few frames later, but it gives me extremely like effective way of controlling the maximum amount of casts executed in one frame. So this is very like a short description of physics in the game, but this touches very common problem in games when we are executing too much casts and too much physical requests in one particular frame. And it is like in many games that we need to have a middle layer between gameplay code and physics engine to control the number of casts. And it gives us really that command queue with batched execution of casts. It gives us really nice control for the maximum amount of casts performed in one frame. And now we are going to the last chapter in our presentation. This is about optimization. So this is like very common in almost every game that we are using a distance to camera to try to optimize like logic, higher level logic in the game. So let's say we have the hero, and we can like decide if we want to play the sound or play some special effect depending on the distance from the camera. So we are just doing it in a close range to the camera. Also, we can use distance to camera to lower some quality for specific things. So for example, for farther objects, we don't need to have the same animation quality for these objects, or we can switch to lower polygons for visual meshes. This is something that could be done very easily with the distance to camera, and we are avoiding some performance hit because of that. And also we can lower the frequency of AI or logic updates depending on the distance to camera. So farther we are from the camera, we are updating specific objects with lower frequency. And we can go even further with that. So we can kind of define like specific classes depending on the distance from the camera. Objects closer to me, I will update every frame because they need to be high quality because they are very close to the hero. But objects farther away, I can update every 2 frames or every 3 or 4 frames farther they are from the camera. So here on the right is very simple code how we can do it. The only thing that you need to be careful here is to be sure that in a specific class that you are actually not updating all objects in one frame. So for example, for objects that should be updated every 4 frames, that you end up updating all these objects in one frame, and then for 3 frames you are not updating any of them. So then you have like performance hit on that one specific frame. What we should do here, we should rather spread the update of these objects on several frames, so that we are not updating all of them on one frame and doing nothing in the next frames. So to do it, for example, we can use some unique object ID for these objects and like compute, let's say, kind of slot when in the frame count these objects should be updated. So in this way we are uniquely spreading these objects across several frames. And this is something which is also kind of connected to the same problem and solutions. I call it like one per frame policy. And it comes from the fact that everything what I was talking about with optimization and physics was trying to actually avoid unstable frame time. So the situation when we are doing a lot of things in one frame and very little in a few frames after it. So it creates that kind of situation that we have like a hitch. So we have one very long frame which kind of freezes the game, and then we are doing almost nothing in the next frames, which are like very simple. So what we should try to do instead, we should kind of try to spread that work, not doing everything in one frame and almost nothing in next frames, but just spread the work into smaller chunks and spread it across several frames. It gives us maybe like slower frame rate overall, but it is much more constant frame rate, and it is usually way much better to have like stable frame rate instead of some like random hitches somewhere along your timeline. So for example, for explosions or any other like costly operation in your game, for example, some activating sounds or activating objects or any kind of like operation that has significant cost, we could have just like a global counter, how many times that specific thing was executed in one frame, and just avoiding doing the same thing again in that one frame, and just delay execution, make some queue to execute, to trigger that thing just one frame later. And usually, for example, for explosions, nobody will notice that you are not exactly executing two explosions on the same frame, and you can execute them just one frame later. So we have still two explosions, one on the previous frame, one on the next frame, and you are not like trying to execute too much code in one frame, and you are, this case, you are effectively avoiding big hitches in your performance. So summarizing this optimization chapter, so using distance to camera is really very effective way of like optimizing your game, and it is used really like everywhere on many different things. And what you should do with your higher level logic is trying to spread the work on several frames, so divide your big task into smaller chunks. And for example, one per frame policy can help you to spread the work over on several frames in your game. So in this case, you are getting much more stable frame rate, and you are avoiding performance hitches. So that was the last chapter in my presentation. So just a short recap of our gameplay programming patterns. So at the beginning, I talked about arrays, so how they are really the most common structure in game or gameplay programming, and it is really important to be familiar with arrays. And later, I talked about how to design your data, how to design them in like kind of friendly way for designers, how we can avoid like performance hit for spawning and despawning objects, and use pre-allocated pool of objects. Then I talked shortly about movement prediction, which actually we are using much more often in gameplay programming than we could expect. Then very important idea, concept of state machines, and how to encapsulate gameplay features as state in state machines. Then about physics and optimization, how to control the number of physical casts you want to perform in one frame using some command queue and the middle layer between your gameplay logic and physics engine. and all the tricks for optimization, which is just really opportunities to do less work than needed. So thank you so much for this presentation. I hope you enjoyed it. And even if you knew some of these concepts, you still could learn something new from that presentation. And if you have any questions, I'm really happy to answer all of them. Thank you so much.